Web-assigned two-dimensional momentum, problem number 3. We have the battling cars. We have one car that's moving directly northeast. Whoa. Okay, stuff on the table here. All right, so this is going to be M1 V1. And it's, given at 45 degrees. So there you go. And then it hits another car of a different mass, and they stick. So it's an inelastic collision. And the information of this is given. The information for the other car is given, its mass and velocity. It's due south, so its momentum looks something like this. This is M2 V2. You can also call this momentum number 2. You can call this momentum number 1. Mass times velocity. And so the final momentum is going to look like this. This is momentum total. And of course then it's also equal to momentum total prime, the momentum after the collision. It consists of both masses moving in this direction. So theta we're looking for, and the speed we're looking for as well. Not the momentum, but the speed. So what we want to do, again, is realize that the momentum in the x and the momentum in the y have to be treated separately. So let's go ahead and do that. Momentum total in the x is equal to momentum 1 in the x plus momentum 2 in the x. Simple as that to begin with. And that's then going to be equal to M1 V1, M1 V1. But in the x, it's just the component that's in the x direction. So that's cosine of, I'm going to go ahead and put 45 degrees. Cosine of 45. The fact that it's 45 makes this a little bit nice because we know how much, what size that component is. Now, momentum 2 in the x. How much of car number 2? When I didn't show the picture of the cars, I'm showing the momentum of car 1, momentum of car 2, and when they collide, the sum total is this. So we don't have to draw an elaborate picture. But how much momentum car 2 is in the x? Well, it's 0. All right, so this then is equal to M1 V1. Now, cosine of 45 is the same as dividing by square root of 2. So that's momentum total in the x direction. That's pretty important. You have all these numbers. Momentum total in the y is equal to momentum 1 in the y plus momentum 2 in the y direction. That's equal to M1 V1 sine of 45 degrees. See, momentum 1 in the y, it's, the vertical component of this. So that's M1 V1 sine of 45. The momentum of car 2 in the y direction, well, actually it's going downward. So I'm going to, this is upward. We'll call that positive. Positive upward, then this would be negative. So you have to subtract off M2 V2. All of it. All right. So that's M1 V1 sine of 45, like divide by the square root of 2, minus M2 V2. And that is momentum total in the y direction. So now you have those two things. You have the numbers. Plug your numbers in. And then putting it together, we have momentum total in the x. We have, I don't know how big this is. I think these might be reasonable depending on your numbers, right? Maybe momentum total in the y actually goes upward. I don't know. Depends for you. And then, of course, we get momentum total. And that's momentum total after as well. So if you're worried about that. So the answer to you have the total momentum before and after being the same. We're just trying to figure out now, after they collide and stick, what's their speed, what's their direction. So we got to be still a little careful here. Momentum total. Just looking for the magnitude now. is equal to the square root of momentum total x squared plus momentum total y squared. You have those two numbers. Then, you're not done. The v that you're looking for, the velocity, speed in this case, you're looking for the speed of the two cars together. Well, speed is equal to momentum over mass. Momentum is mass times velocity. So that's equal to this, basically total, right? It's the total momentum divided by m1 plus m2. So that's going to be your answer. This is your answer, not the total momentum. And finally, theta. Theta is equal to inverse tangent of opposite over, here's theta, right? Opposite over adjacent. Momentum total y over momentum total x. And there's that part of the answer. So you see a common theme here. What we've done so far in the analysis of two-dimensional momentum problems, you have to treat the x and the y, take information about those things separately, and then you have to differentiate also between the total momentum versus speed. Speed and momentum are not the same thing. So we had to divide by the mass to get the speed once we had the value of the momentum. Hopefully that makes sense. See you later.